In this lecture, we are going to discuss about the two types of MOSFETs as well as current conditions and conditions for triode region and etc. So what is this N-channel MOSFET or NMOS is? The channel is, the moment a p-type substrate is becoming N-type channel, so there is a channel of electrons. That's why it is called NMOS transistor or NMOS. Now if it is a p-channel MOSFET, so substrate is N-type, so this N-type will become the p-type by beneath this layer. So there is a channel length of L, and in this channel length L there is a number of holes present in this channel, so that's why it is a p-channel MOSFET. Now to make a channel we need at least VGS is at least VTN, or at least it should be greater than or equal to VTN to induce a channel. But if we see for PMOS, generally how it will become when VGS is negative, so negative will be formed here, then negative to negative will repel each other, then it will become positive ions in this channel. Then when we apply more negative voltage here, the positive holes in the N-type substrate will come to the near to this oxide layer, and similarly P holes from these two regions, then it will become the strong inversion of the P. Now for strong inversion VGS should be more negative, that means the threshold voltage of PMOS should be negative. So to make the this is VTN, for VGS should be greater than VTN. So without confusion, what we will do is VGS mod VGS should be greater than or equal to mod VTP, or we can say VSG should be greater than mod VTP, or we can say VGS should be more negative than the VTP. So because VTP is negative, so I think this is one is very good, because so without any confusion we will take mod of this, then make as TP. So now we'll have for cutoff regions this VGS should be less than VTN, or we can say mod VGS is less than mod VTP for cutoff region. Now condition for triode region is VGS is greater than VTN, so we should apply more VGS threshold, more threshold voltage, and VDS should be very small, or we can say VGS minus VT. So VDS is VGS minus VT. So this is condition for triode region, or we can say linear region. In linear region, what is the current equation is mu1 Cox into W by L VGS minus VTN into VDS minus VDS square by 2. So the current direction is from drain to source. Reason is, so whenever this electrons coming from source to drain, the current direction will be opposite, that is drain to source. But in the case of P channel, so conditions is mod VGS is greater than mod VTP, or we can say VSG should be greater than mod VTP. And the second condition is, if we take both are mod, so mod VDS is less than mod VGS minus mod VTP, or we can say VSG is less than VSG minus mod VTP. Current equation is mu P Cox, so it will come now here mu1 Cox, now it is mu P Cox W by L. Now this is again same, I can take mod VGS, or we can say VSG minus mod VTP into VSD minus VSD square by 2. Now current direction in this case this will become source to drain, because from source region the holes are coming from will reach from source to drain, so the current direction is same, that is source to drain the current direction. So this is the current expressions. Next we will see for condition for saturation regions. For NMOS, VGS is greater than VTN, one condition, and VDA should be greater than or equal to VGS minus VT. This VGS minus VT we will call as overdrive voltage VOV. So overdrive voltage VOV. So condition for saturation is these two conditions. Now ID is equal to, in this case, whenever VDS is equal to VGS minus VT, from the previous expression we will get this expression, that is mu1 Cox by 2 W by L VGS minus VTN whole square. So generally we can have the other notation as Kn dash by 2. So Kn dash is nothing but mu1 into Cox into again VOV whole square. In some cases we can replace this total term by K also. If it is a PMOS, same, we will take either mod or VSG is greater than mod VTP, or VSD is greater than or equal to VSG minus mod VTP, or we can take both mod for these two conditions. ID is equal to same Kp dash by 2 W by L VOV whole square or VSG minus mod VTP whole square. Now when we see the symbols, we will have so many symbols, approximately 5 symbols. This one is normal, we will use generally. So drain is always up, gate and source. So for source I will give the current direction. So drain to source current direction is gate. What is this gate current is 0 always, because there is no this is a dielectric material, so no, there is no current flow in between these two. So Ig is 0, so ID is equal to Is, I can say. Now other symbol is, so we'll have 4 terminal device, so bulk is also there and the direction is outward of the source. Or we can say same symbol, but if you give the direction to the bulk, it will be inward to the base, I mean not base, bulk. And one more is there, so 3 dots will be there, so for each there is a drain, bulk and source, and outward, or we can say inward also. There is one more, without any direction, if I use like this, for this I need to use the PMOS as like this. So there is a bubble in this is upper PMOS, without bubble we can say NMOS. So many symbols, so depending on the application or depending on the question they will give. Similarly, if it is a PMOS, always the source is at the top, that is it will be at higher potential, the source will be at lower potential when it is in NMOS, because VGS should be always positive. In this case VSG should be positive, VSG, or VGS is negative. So when this will become negative is VG minus VS is equal to, so whenever VS is higher potential, then only we will get negative voltage. So that's why source is always higher potential, so that's why this is top always. So remaining symbols we can now compare with these two. Now we have one more parameter, very important parameter, we can call it as a transconductance. What is this transconductance is? See, the drain current is controlled by the VGS, that is input voltage. So I versus V, output is current, input is voltage, so I by V is the transconductance. So in saturation region, if I find transconductance, that is delta ID by delta VGS. For small VGS, what is the current change? Now if I differentiate this equation with respect to VGS, I will get this, that is Kn dash into W by L into VGS minus VT. This is one expression, so we will have 2-3 expressions for this one. If I use this expression 1 and find VGS minus VT, that is 2 ID by Kn dash by 2 by L square root. Now if I replace this VGS minus VT here, I will get 2 Kn dash W by L into ID. One more equation I will get here is, from this Kn dash, from this expression, if I use Kn dash W by L, that is 2 ID by VOV square or 2 ID by VGS minus VT whole square, I can replace in this GM Kn dash W by L, then I will get 2 ID by VOV. So there are 3 expressions we will get: Kn dash W by L VOV, 2 into Kn dash W by L ID, and 2 ID VOV. So we can use, depending on the application, I can use this GM. So generally we can use this, because GM is square root of this current direct. So generally we use current biasing technique, so this is most preferably we use. Now one more we have to find is, in linear region, so the current is linearly proportional to this VDS. If I use VDS is very much less than VGS minus VT, I can neglect this term. Now if I want to find the RDS, the resistance, so delta ID by delta VDS if I use, so I will get, so depending, so this VDS will be 1, so this will become mu1 Cox W by L into VGS minus VT. So I need, this is not RDS, this is 1 by RDS. So this RDS, what I will get is delta VDS by delta IDS, it is 1 by mu n Cox W by L into VGS minus VT. This is in what is this region? Linear region. So this is also one important parameter. Frequently they will ask what is RDS. So in linear region this will become mu1 1 by mu1 Cox W by L into VGS minus VT. In the next lectures we will see the small signal models of a MOSFET.